Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Algebra 2 class. Okay, guys, today we're starting my favorite chapter, um, period. I love graphing. I'm big on graphing, not just linear equations, but just any kind of function I like to graph. It's kind of like making a puzzle for me. So I'm going to be really excited about this. I hope you guys can get my enthusiasm, and I hope you guys can really understand all the intricacies, okay? I know that I tend to repeat myself a lot, and I'm going to do it one more time today, right now. I always start every chapter by saying, okay, guys, this is really important for the rest of the chapter. I don't say that just because I want to say that or I want to hear myself say that. I say that because it is extremely important. And if you guys have noticed so far, okay, we're entering our fourth chapter now, have not all of the chapters built on each other? Right? Bless you. We learned fractions the first chapter. We've been using fractions the whole entire year so far, and we're going to continue to do so, etc., etc., etc. We learned how to solve equations now. We did word problems. We're going to need those skills for the rest of the year. This also will be used for the rest of the year. Actually, this here will be used for the rest of your math career for the next 2 years of high school plus your next 2 years in college. So let's learn it today the right way. First of all, when we're talking about ordered pairs and graphs, guys, we're dealing with what's called a coordinate axis, okay? This is called a coordinate axis or a Cartesian plane. Coordinate axis. It's also known as a Cartesian plane. Now, the reason that it's called a Cartesian plane is because there was a gentleman by the name of Descartes back in France, okay, in the 1600s, actually maybe even a little earlier. But this dude was kind of bored, legend has it. This is the story. And remember, guys, back then they didn't have iPads or computers or anything to entertain you. So they had a lot of time to think, which was a great thing. That's why we have so many inventions back in old times because what is it? There's a phrase that says necessity is the mother of invention. So they needed things to make their life easier, so they invented things. Anyways, supposedly the legend has it he's in his bed, he's lying down, he's just looking up at the ceiling, and he sees a fly going from one point to another point on his ceiling. So he was kind of bored. So he starts marking all the points that the fly would come to. And eventually his whole entire ceiling was just this huge grid with a bunch of dots. So he wanted to organize these dots. And upon organizing these dots, he invented and came up with the Cartesian or coordinate axis plane, which is an x and y two-dimensional axis. Okay, the x-axis is a horizontal axis, and it includes the values that are called the input, the independent variable, or the domain. The x-axis includes all of those variables. Okay, it's all the same thing. The x-axis is horizontal. I always remember that the x-axis is horizontal because it is like the horizon. When you go to the beach, you look out into the ocean, you see the horizon and it's horizontal like the x-axis, okay? The y-axis, let me erase all this stuff. The y-axis is the output. It's called the dependent variable, and it's also known as the range. We're going to get into all of that vocabulary, heavy into it soon enough. But right now, we're just learning what this Cartesian plane is. So I have the x-axis, which includes what's called the input values, the independent variable, or the domain. Those are the x values on the x-axis. That's what they're called. The y-axis, that is a vertical, up and down, kind of like columns hold up roofs and ceilings. Vertical. Okay, that is the output, the dependent variable, and the range. Now, in this x and y axis, guys, you have where the x and y intersect, this little red dot here, and that's called the origin. The origin's values are 0, 0. because it is the point where x is 0 and y is 0. It is where they both intersect, and that is called the origin of the graph. Any other point on this graph, like this blue one, is called an ordered pair. It is called an ordered pair because it will go in alphabetical order, x comma y, always, no matter what. That's the ordered pair. So in this particular case, this ordered pair is 4 comma 3. Why? Because I went 1, 2, 3, 4 on my x, and I went up 1, 2, 3. And in a nutshell, that's the Cartesian or coordinate axis plane. It's the x and y axis. Make sense so far? Pretty simple, right? Okay. Remember, as a domain, get this definition now because we're going to use it a lot. The domain refers to all possible x values or all possible input values in a given function. And we're going to talk about what a function is soon enough. And the range is representative of all of the possible y values or the output values, okay, in a particular function. We don't need to know much about this right now, but just keep this in mind. Domain, all possible x values. Range, all possible y values. Now, in a Cartesian plane, there are 4 quadrants. This is the way the quadrants go. No, this is not a typo. It goes counterclockwise, okay? Counterclockwise. So you have quadrant 1. And under quadrant 1, I have a little plus plus. Because in quadrant 1 here, guys, what's happening is everything here is positive. My x values are positive. My y values are positive. So any point inside of quadrant 1 is going to be a positive x and a positive y, period. For quadrant 2, well, remember that this is my origin here in the center. So to the right of the origin and above the origin, I'm going positive and positive. Hence why the x and y ordered pair in any ordered pair in the quadrant 1 is positive, positive. For quadrant 2 here, I've got going to the left, which is negative. So all of my x values in quadrant 2 are negative, but I'm going up from here, so that's why I have negative x's and positive y's. All of my ordered pairs in quadrant 2 will be negative, positive. In quadrant 3, once again, I'm going to the left of the origin, negative x, but I'm going below the origin, going below 0, that's negative, so negative y. So in quadrant 3, all ordered pairs are negative, comma, negative. No matter what. There's no exception here, guys, okay? And in quadrant 4, I'm going to the right, once again, positive, so hence a positive x, but I'm going down, so it's negative, okay? So that's the signage of the 4 quadrants. Now, when you're on the actual axis itself, you're not in any quadrant. You're on the axis. Big difference. For example, this point right here. This point right here is 3 comma 0. That doesn't belong to any quadrant. That's on the x-axis. This point right here is 1, 2, 3. This is 0, negative 4. X is 0 here, y is negative 4. That's not in any quadrant. That's on the axis. So the quadrants obey these positive and negative laws, but when you're on the axis, just read where you are. Does that make sense? Okay. Now, let's graph each ordered pair. Should be simple. This goes way back to pre-algebra, okay? So 1, 5, 1 on the x, 1, 2, 3, 4, 5. Perfect. Negative 2, 0, that's on the x-axis. Perfect. Negative 1, negative 3, I go negative 1 on the x, so negative 1 to the left, and I go down 1, 2, 3, negative 1, negative 3. 0, negative 4, 0 on the x, negative 1, 2, 3, 4 on the y-axis. And negative 4, 2, negative 4 on the x, 1, 2, 3, 4 to the left, up 1, 2, negative 4, 2. It's that simple. Does everyone remember how I graph those? Well, right, guys? I went kind of quick here because should be common knowledge. Yes, no, maybe kind of, sort of. Okay, move on then. Right, I don't want to bore you. Thank you. Okay, next. Identify the coordinates of each ordered pair in the Cartesian plane. Okay, let's see what we got here. A, what would the coordinates of A be here? Negative 3. Negative 3, 3 is exactly correct. Perfect. How about B? How about B? Yes, negative 4, negative 4, negative 4. Thank you. C. 3, 0. Yes, that is on the x-axis, 3, 0. D. 6, 5. Yes, because I went 6 on the x and up 5. Thank you, 6, 5. Beautiful. E. Nope, it won't be 5, 3. 5, negative 3. Yes, sir. Very good. Good mistake as well. That's how we learn. And F, last but not least. 0, negative 5. Oh, that didn't come out too professional. 0, negative 5. Very good. Does that make sense, y'all? Someone said 6. Let me say 1, 2, 3, 4. No, it's 5. Thank you, guys. Easy peasy, right? All right, let's do this. Now, we have already worked with equations in one variable. We know that. Today, we will begin to examine equations in two variables. Solutions to equations in two variables satisfy the equation. In other words, it makes it a true statement. When you have a solution, okay, guys, just like when you just have one variable. If it was x plus 5 equals 9, x is 4. Because when I plug that value of x in, it makes a true statement. Well, now we're dealing with two variables. We're going to be dealing with x and y. A solution to an equation that has more than one variable, same thing. It's the value, in this case the ordered pair, that makes the equation true. It satisfies the equation. In order to verify whether or not an ordered pair satisfies or is a solution of a given linear equation, simply evaluate the equation using the given ordered pair. What's happening here? Okay. We're gonna get to graphing real soon, but they're kind of telling you to walk before you run. I don't know if you guys remember, but I can go ahead and solve this bad. Sorry about that. I don't know if you guys can remember, but I can solve this for y and put this into y equals mx plus b form. And then I can graph the y-intercept and follow the slope. From the faces that you're all looking at me with, you're telling me no, but I'm telling you yes. You saw this in pre-algebra, you saw this in algebra, you saw this in geometry. We're going to revisit it, of course, but that's where they're going with this. But before we can graph, you got to understand what solutions mean. So they want to know, does 4, 1 satisfy the equation x plus 2y equals 6? Literally just plug it in. Okay, yes, it does. This is x, this is y. Plug it in. 4 plus 2 equals 6. Yes, it does. So this is a solution. If it does not satisfy the solution or the equation, then it is not a solution. Determine if the following ordered pairs satisfy the equation x plus 2y equals 8. Okay, 2, 3. Let's see if that one works. We got 2. Oh boy. We've got 2 plus 2 times 3, which is 6. That equals 8. Yes. We've got 6 plus 2 times negative 1. That's 4. So that's no, not a solution. And then I've got negative 2 plus 2 times 5, which is 10. That equals 8. So that's a big fat yes as well. So when you're trying to determine whether or not an ordered pair satisfies a linear equation, literally, simply, just plug it in and solve. Okay, so does that make sense, guys? You literally just plug it in and you find the solution. Okay, next. Now, creating a table. Okay, guys, let's explain this. Let me explain all of this good stuff. We're not going to need a table for linear equations when we start graphing them for real because we have different skills. We can find the x and y intercept, or we can write the equation in slope-intercept form, graph the y-intercept, follow the slope both forwards and backwards, and you graph. However, not all functions in the world are a linear function that's nice and easy like that. So whenever you're in a situation where you have to graph, okay, make a table. And when you're making a table, remember what I had told you. X is independent, okay? That means it can be anything it wants. When you go to a store, and let's say you go to McDonald's just to make life easy, and let's say you're going to get the number one meal, and let's just say for argument's sake that it's a $5 meal, okay? You go in, there's a function that computer has. It says y equals 5x. For every burger that you buy, they plug it in, it plugs in for you into the computer, the one, and it rings up, oh, it's $5. It wasn't magic that allows that to happen. There's a function, okay? And that x is independent because I can go in and I can buy one burger meal, but you can go in and maybe you're really hungry that day and you buy two. Maybe you got to go and buy for your whole team, so you got to buy 32. Maybe you go and you're just going to go and you're going to buy for your friends, so you buy 5. The number of meals that you buy is independent. And that's what I want you to think about when you're thinking about x. X is an independent variable. You go to the movies. You show up to the movies. You're there with your friend, your girl, your family, whatever. You get to the movies and you're like, oh, man, I don't really like any of these. You can walk away. You spent nothing. Or you could end up buying one ticket. Or you could be nice and buy a ticket for you and your friend or you and your girlfriend. Or you say, no, Mom and Dad, I'm going to pay for today. Regardless, that's up to you. That's what independent means. Sorry about that. So table method. First, solve the equation for y. You always want to try to solve for y, guys. It's going to make your life easy. Then simply create an x and y table. You're going to see below what I mean by that. And choose values for x. X is the independent variable. So you can choose any value you want for this, guys. Then evaluate the function for the values of x that you have chosen. I like to use what we call the moral 5. I did not come up with that. One of my kids came up with that a while ago, and I used the moral 5. And the moral 5 is -2, -1, 0, 1, and 2. If the coefficient of x is a whole number, okay? If the coefficient of x is a fraction, then use x values that are multiples of the given denominator. And the reason I tell you to do that is so you don't have fractions. It's almost impossible to graph a fraction. You'd have to estimate, and I don't want you to do that. So, what do I do here? Okay, I want to make a table of values for each of the equations here. First thing I'm going to do is I'm going to solve for y. So how do I solve for y here? So you subtract 2x to both sides. Very good. So y equals -2x plus 8. Now, I got to make a table of values. I'm going to use the moral 5. So -2, -1, 0, 1, and 2. When x is -2, plug that in. What's y? No. When x is -2, -2 times -2 is 4. 4 plus 8 is 12. So I've got -2, 12. Now, what did I do there? I literally just plugged in the value of x into the function. And 4 plus 8 would be 12. When x is -1, what's y? Yeah, 10, because I got -2 times -1, which is 2. 2 plus 8 is 10. So I've got -1, 10. When x is 0, what's y? That's right. So I've got my ordered pair 0, 8. When x is 1, what's y? 6. Very good. And when x is 2, what's y? 4. Pretty simple, right? Yes, sir. Okay, it depends, right? The question was, does the 2x here always turn into a negative? In this case, yes, because I get rid of a positive with a negative. Right, my brother? Good question. I always want to get y alone, so I'm going to use my equation skills to solve for y. Yes, sir. And a linear function, there's always a pattern, yes. And there's always going to be a pattern when you use the moral 5, yes. No, it won't be the same pattern. Very good question, son. Thank you. Now, this occurs here, guys, when, as you can see, the coefficient, that's the number in front of x, is a whole number, or a whole unit, rather, an integer. Let's see what happens when it's a fraction. Let's go ahead and solve here. I'm going to add 3x to both sides. So I've got 2y equals 3x plus 11 divided by 2. Y equals 3 halves x plus 11 halves. That makes life very difficult. Okay? That makes life very difficult. And actually, you know what? I'm going to make this more complicated than it has to be. Change this to a 12. Let's change that to a 12. So then I have y equals 3 halves x plus 6. We're already dealing with a fraction. Let me let you walk before you run. Okay. When I have a coefficient in front of x that's a whole number, I'm going to use the moral 5. However, when I have a coefficient of x that's a fraction, guys, the moral 5 just isn't going to cut it. You're going to get accurate values. That's fine. But for example, if I use the moral 5 here and I choose for x when x is 1, you got 3 halves plus 6. So 3 halves plus 6 is going to be 15 halves, which is going to be 7.5. Can you graph 7.5 accurately on a graph? No, unless you do all of your intervals by halves. But that's going to be really time consuming and almost impossible for later on. So to avoid this problem, we're going to use multiples of the denominator that is being multiplied to the variable. Yes, sir, you have a question. You don't use even numbers. I did not say even numbers. In this particular case, it'd be even numbers. But you don't use even numbers. You use multiples of the denominator. So in this case, the multiples I would use, -2, -4, 0, 2, and 4. Those are the easiest. Yeah, I could have gone -4, -2. Yes, I should have. So let's go that route, sir. And thank you. So -4, -2. So, okay, so when x is -4, let's do the math here. We got 3 halves times -4 plus 6. See how much easier this is? This is -12 divided by 2, which is -6. And -6 plus 6 is, so -4, 0. Boom. When x is -2, what do you got? 3 times -2 is -6. -6 divided by 2 is -3. -3 plus 6 is 3. So this is -2, comma 3. When x is 0, what's y? When x is 0, y is 6. Very good. When x is 2, what's y? We got 2, yep. When x is 2, y is 9. When x is 4, what is y? 4, we got 12, 6. No. No. When x is 4, what's 3 times 4? 12 divided by 2 is 6 plus 6 is 12, not 9. 4, 12. Does this make sense, guys? Yes, sir. What? Sorry, here. My bad. Thank you, kid. Thank you. Does that make sense? Yes, sir. Okay, the question is, can I cheat the system and just go through the pattern and not learn anything? No, I do not want you to do that. I want you to go through the actual numbers because, guys, is life always going to be pretty and beautiful like the moral 5 or like the pretty pattern that we have here? What if you're on the SAT and I tell you, I give you this, but instead I tell you values to plug in. I tell you, plug in when x is -11, when x is 15, when x is 26, and when x is 9. Will your little pattern method work, sir? No. How about we do exactly what I say to help you guys and not look for a shortcut, not look for a trick. Not look for an escape, but actually do the math. Please and thank you, gentlemen. Okay. Now for C, what do we got here? Who can solve for y for me here? What does y equal here? Yes, sir. Y equals negative 4/3 x plus 3. Okay? Let me show you how we got that, because a lot of people gave me the wrong thing here. Subtract 4x, good job. That's exactly how you start. So you got 3y equals negative 4x plus 9. Go ahead and divide everything by 3. So y equals negative 4/3 x plus 3. Very good. Now here again, I'm not going to use moral 5 values, because the moral 5 values are going to lead me to a lot of nasty fractions, and it's almost impossible to graph nasty fractions. Also, why would I want answers that are nasty anyways? I want to try to make my life easy. So I'm going to use, in this case, I'm going to use negative 6, negative 3, 0, 3, and 6. So when x is negative 6, what's y? It's going to be 11. Very good. Because negative 4 times negative 6 is 24. 24 divided by 3 is 8. 8 plus 3 is 11. Very good. What about when x is negative 3? We've got 7. Yes, it is. Very good. When x is 0? That's an easy one. When x is 3? We got negative 1. Very good. And when x is 6? Negative 5, because you got 4. Negative 4 times 6 is negative 24. Divided by 3 is negative 8. Negative 8 plus 3 is negative 5. Make sense? Yes, sir. Of course. The question is here, thank you so much for your honesty, is why did you not choose the moral 5 here? Why did you use negative 6, 3, 0, 3, and 6? Don't I have a denominator here? Don't I have a fraction being multiplied to the x? So whenever I have a fraction being multiplied to the x, whenever that's the coefficient, I'm going to choose multiples of the denominator. Why, Moro? Why? Let me show you. Let's go ahead and use when x is 1. Okay? If x is 1 here, we've got y equals negative 4/3 times 1 plus 3. I have no problem doing this. This is negative 4/3 plus 3 over 1. That goes to a 3. That goes to a 9. So that equals 5/9. So when x is 1, y is 5/9. Now, real quick, let's go back here for a second. The point was 1 5/9. So x is 1. 5/9 would be, I don't know about there. Is that an accurate measure for 5/9? No. Not because I'm a bad artist, just because I don't have a built-in ruler in my head. You would need a ruler to get 5/9 from that. Do you see what I'm saying? So whenever, guys, whenever you're making a table, that's why I write things out for you guys. If the coefficient of x is a fraction, then use the x values that are multiples of the given denominator. So for this particular case, my brother, again, thank you so much for your honesty. My denominator here was 3, my man. So I used multiples of the denominator. Negative 6, negative 3, 0, awesome, 3, and 6. Does that make sense? Promise? Okay. Everyone, I'll give you 2 minutes. Go, fill out this table. For D, please. Make a table. Let's go. Yes, sir. Oh, you got it? Tell me. You're going to use the moral 5 for this one, right? So I got negative 2, negative 1, 0, 1, and 2. Talk to me, brother. So negative 2, 13, okay. And that is correct. Negative 1 comma 8. When x is negative 1, you plug that in. Y is 8. Yes, sir, my brother. Can continue. You darn right. You got 3, 0, 3. Excellent. And then when x is 1, we got y is negative 2. Fantastic. And then this one is what now? Negative 7. That's exactly right. Make sense? All right. All right, let's see what else we got here. All right, we got 2 more pages. All right, we're going to wrap up here for today, and we will continue with graphing applications. Thank you very much. There is technically no homework today because we did not finish the lesson. All I ask you to do is please make sure you can make a table of values right now. Make sure you can graph ordered pairs. Make sure you know where all the quadrants are. And make sure you know that the x-axis goes horizontal and the y-axis vertical. Thank you so much. Just go over today's notes. Make sure you know them. God bless you. Hope you learned a lot. Have a great day. Bye-bye.